Okay, so we're here in to start out with objects. To start out with objects, we're going to be using this Thinking in Java 3rd edition revision 4. Okay, it's an open source textbook for Java. So let's start out with an introduction to objects. So he writes, we cut up nature, organize it into concepts, and ascribe significances, as we do largely because we are parties to an agreement that holds throughout our speech community and is codified in the patterns of our language. We cannot talk at all except by subscribing to the organization and classification of data which the agreement decrees. Benjamin Lee Wolfe, 1897 to 1941. The genesis of the computer revolution was in a machine. The genesis of our programming languages thus tends to look like that machine. But computers are not so much machines as they are mind amplification tools. Bicycles for the mind, as Steve Jobs is fond of saying, and a different kind of expressive medium. As a result, the tools are beginning to look less like machines and more like parts of our minds, and also are like other forms of expression, such as writing, painting, sculpting, animation, and filmmaking. Object-oriented programming, or OOP, is part of this movement towards using the computer as an expressive medium. This chapter will introduce you to the basic concepts of OOP, including an overview of development methods. This chapter and this book assume that you have had experience in a procedural programming language, like JavaScript, although not necessarily C. If you think you need more preparation in programming and the syntax of C before tackling this book, you should work through the Foundations for Java training CD bound in the back of this book. We don't need that. We've already done plenty of programming at this point. This chapter is background and supplementary material. Many people do not feel comfortable wading into object-oriented programming without understanding the big picture first. Thus, there are many concepts that are introduced here to give you a solid overview of OOP. However, other people may not get the big picture concepts until they've seen some of the mechanics first. These people may become bogged down and lost without some code to get their hands on. If you're part of this latter group and are eager to get to the specifics of the language, feel free to jump past this chapter. Skipping it at this point will not prevent you from writing programs or learning the language. However, you will want to come back here eventually to fill in your knowledge so you can understand why objects are important and how to design with them. Okay, so we already have some experience programming in Java. It's now an appropriate time to introduce objects. Okay. The progress of abstraction. Okay. All programming languages provide abstractions. It can be argued that the complexity of the problems you are trying to solve is directly related to the kind and quality of abstraction. By kind, I mean, what is it that you are trying to abstract? Assembly language is a small abstraction of the underlying machine. Many so-called imperative languages that followed, such as Fortran, BASIC, and C, were abstractions of assembly language. These languages are big improvements over assembly language, but their primary abstraction still requires you to think in terms of the structure of the computer rather than the structure of the problem you are trying to solve. The programmer must establish the association between the machine model in the solution space, which is the space where you are modeling that problem, such as a computer, and the model of the problem that is actually being solved in the problem space, which is the space where the problem exists. The effort required to perform this mapping and the fact that it is intrinsic to the programming language produces programs that are difficult to write and expensive to maintain, and as a side effect created the entire programming methods industry. Okay guys, so if you were taking notes on this, you might want to write down the word abstraction, because abstraction is the first main vocabulary word in that section. Okay? Alright, you may have to look it up later on to get a good definition of it. The other thing you might want to write down is solution space. Okay, So that is the place where you're modeling the problem. For example, when you write code in your IDE, that's your solution space, right? You are creating a solution to some problem, right? Okay. The problem space would be like wherever the problem is occurring, right? If it was, if you're writing a grading application for a teacher, that's the problem space. That's the procedure that the teacher is going through that you're solving by writing a program to automate it. That's the problem space, right? The solution space is your code and the program you're creating. Okay. With abstraction is basically, it's not machine language, right? We write commands that write machine language for us. So when you take a step back, every time you take a step back from that, it's an abstraction, right? You're not writing ones and zeros, you're writing commands that are human readable, right? That's abstraction. Okay? It's making the computer commands abstract in a way that you can understand. Okay, that's abstraction. Okay. Alternative to modeling the machine is to model the problem you are trying to solve. Early languages such as LISP and APL chose particular views of the world. All problems are ultimately lists, or all problems are algorithmic, respectively. PROLOG, prologue, casts all problems into chains of decisions. Languages have been created for constraint-based programming and for programming exclusively by manipulating graphical symbols. The latter proved to be too restrictive. Each of these approaches is a good solution to the particular class of problems they're designed to solve, but when you step outside of that domain, they become awkward. So an example that you're familiar with there might be an App Inventor or Scratch, right? Those are manipulating graphical symbols to create a program. Okay, but as you've seen, it has limitations, right? Okay. The object-oriented approach goes a step further by providing tools for the programmer to represent elements in the problem space. This representation is general enough that the programmer is not constrained by any particular type of problem. We refer to elements in the problem space and their representations in the solution space as objects. Okay. You will also need other objects that don't have problem space analogies, analogs. Okay. So let's talk a little bit about what he just said about objects. Okay. So if I wanted to have a program that turned on, say, modeled a light bulb. A light bulb is an object in the problem space. It's right there. I can see it. Okay? In the problem space, there is a light bulb. That's an object, right? You can touch it, you can hold it, it's a light bulb. Okay? In my solution space, that's in my program, I also have a light bulb. Okay? And that light bulb is a model of the actual light bulb in the problem space. Okay? So that's the idea. We're modeling our programming after the thing that we're trying to model, right? Okay, in some cases when he says they won't have problem space analogs, well, what happens if you need to do a lot of math? Like, for example, you guys use the math object, right? You needed a math, like, to do powers and to do square roots and stuff like that. Well, some objects just serve a purpose of just you doing things inside the program. In that case, there's no like math object in the real world, right? In the problem space. But in your solution space, you need a math object because you just need it. You need to do things with it, right? Okay. The idea is that the program is allowed to adapt itself to the lingo of the problem by adding new types of objects. So when you read the code describing the solution, you're reading words that also express the problem. This is more flexible and powerful language abstraction than what we've had before. Thus, OOP allows you to describe the problem in terms of the problem, rather than in terms of the computer where the solution will run. Okay, so if I was taking notes, that's a really important sentence. Let me read it again. OOP allows you to describe the problem in terms of the problem rather than in terms of the computer where the solution will run. There's still a connection back to the computer where the solution, there's still a connection back to the computer. Each object looks quite a bit like a little computer. It has a state, and it has operations that you can ask it to perform. However, this doesn't seem like such a bad analogy to the objects in the real world. They all have characteristics and behaviors. So if we get back to our light bulb, right? A light bulb has characteristics. It's a color, right? It can be clear, it can be white, it can be red, right? It has behaviors. It can turn off, it can turn on, it can produce heat, right? Alan Kay summarized 5 basic characteristics of Smalltalk, the first successful object-oriented language, and one of the languages upon which Java is based. The characteristics represent a pure approach to object-oriented programming. One note, any assessment that we have will not cover the history of computing, okay? I don't find it particularly useful. The only thing we're interested in is the utility of using objects for programming, okay? So we would only be talking about objects and object-oriented programming, not the history or names of past programming languages, okay? Those are not interesting to us. Okay. Okay. 1. If I was taking notes, I would write everything in bold here, okay? 1. Everything is an object. Think of an object as a fancy variable. It stores data, but you can make requests to that object. Ask it to perform operations on itself. In theory, you can take any conceptual component in the problem you're trying to solve, dogs, buildings, services, etc., and represent it as an object in your program. So everything is an object. 2. A program is a bunch of objects telling each other what to do by sending messages. So a program is a bunch of objects telling each other what to do by sending messages. To make a request of an object, you send a message to that object. More concretely, you can think of a message as a request to call a method that belongs to a particular object. So for example, with my light bulb, I would say, "Hey light bulb, what's your color?" And inside the light bulb would be this method that says get color. And light bulb would call the method get color, and that would send back to me, "I'm blue." Okay? That's basically it. Number 3, each object has its own memory made up of other objects. Put another way, you create a new kind of object by making a package containing existing objects. Thus, you can build complexity into a program while hiding it behind the simplicity of objects. And we'll get more into that. I know that makes no sense, okay? But essentially they're saying that you can build objects out of other objects, okay? For example, if you were doing objects about dogs, right? You might have an object called dog, and it has 4 legs, and it barks, right? It has a nose and a tail, okay? But then you might make up another object called a poodle, and that poodle has all the same characteristics of dog, but has additional characteristics specific to poodle, right? And you make another object called chihuahua, and chihuahua has all the characteristics of dog, but it has characteristics specific to chihuahua. Okay? All right, number 4. Every object has a type. Using the parlance is a weird word for using the language of object-oriented programming, right? Each object is an instance of a class, in which class is synonymous with type. The most important distinguishing characteristics of a class is what messages can you send it. I know that makes no sense either. Okay. So every object has a type, right? So for example, if I had an object whose type was woman, okay, and I made an instance of that object woman called Pam, okay, and another instance called Nancy, and another instance called Mary, okay, they would all be objects of the type woman, right? But they would each be individual instances of that type, right? All right, number 5. All objects of a particular type can receive the same messages. This is actually a loaded statement, as you will see later, because an object of the type circle is also an object of type shape. A circle is guaranteed to accept shape messages. This means you can write code that talks to shapes and automatically handle anything that fits the description of a shape. This substitutability, he may have made up that word, is one of the powerful concepts in OOP. Bush, I hope that's how you say his name, offers an even more succinct description of an object. And I would write this down if I was taking notes. An object has state, behavior, and identity. This means that an object can have internal data, which gives it state, and methods to produce behavior. And each object can be uniquely distinguished from every other object. To put this in a concrete sense, each object has a unique address in memory. Okay, so that last statement there was pretty confusing. So it means that an object can have internal data which gives it state. Okay, so for example, if we take our 3 objects of type woman, we could say that one of their characteristics might be whether they're sitting, standing, or jumping. Okay? And each individual object can be sitting or standing or jumping at any particular time. So the state of an object refers to all of the current characteristics of that object, right? So that's state, all right? State's used a lot in programming. It just means basically at any given time, what's all the data that defines what that thing is doing at that particular time. Okay? All right, guys, you made it through your first set of notes on objects in Java. Okay? Excellent work. Good job.